And now people are starting to come in.
All right. Okay, so I think we'll start now. Welcome to the current ASEG webinar talk that we're having at the moment. It's part of a series that we've really started to expand on since COVID. This particular talk is hosted by WA, and I'm the local WA chapter president, Todd Majeski. I'll talk for a bit and then we'll swap over to Anshuman Pradhan, and he's from Stanford University. He's got a very, he's got kind of a mouthful, for me at least, a long presentation title, and then seismic inversion of geostatistically complex reservoir facies models with deep convolutional neural networks. And that sounds like it's gonna be pretty interesting. But before we start, I've got to do some, what we call housekeeping in ASEG. And I'd like to, first off, very much thank our corporate sponsors. We got 3 corporate plus sponsors: High Size, Total Seismic, and Bell Size. These are companies and people who are providing us with funds and support that goes kind of globally across Australia to help ASEG do things like what we're doing right now. And besides them, we've got 2 other corporate sponsors that are putting out some good help too: Southern Geoscience and Santos. So again, thank very much for that. And we'll go about a little bit further as to what we do in ASEG that these guys help out in. But before I do that, I'd also like to thank our brand sponsors. And you can see that we've got one heck of a lot of them, and they're all being very helpful. WA has a bunch. I wish I could go through all of them, but I don't have time. But you notice that Sant has a big group too, and New South Wales. And so all these, they support the local teams and stuff like that. And they've really helped out WA, I can say from my experience, and do appreciate that. Now, going back to the webinar, so you'll only hear me yak for a bit, and then it's gonna be Anshuman. So if you have any questions or comments, just click on that Q&A button on the bottom and type in your questions. You won't be able to shout out or anything like that. And then at the end, we'll try to go through and see if we can answer them and review things. So that's our etiquette here in that regard. I was thinking about the webinar series. Here's some new ones coming up just in August so far. These are the most recent ones coming in. So next Wednesday, it's a very interesting one. I would recommend that if you have the chance, go ahead and sign up for this one. It's working with your inner critic. It's that we've hired someone to give us a workshop type presentation, and you know, it's, if you have maybe a whole bunch of self-esteem, you can blow this off. But most people have, you know, a little bit questions in the back of their minds. You're in a critic, like they're saying, or some people, you know, call it the imposter syndrome. It's so neat that we're actually offering people outside ASEG to join this if you want for $25. You could pass that to your friends if you're keen on that. Next, the following Tuesday after that, Alberto Seguro is going to be talking, giving a talk on stochastic inversion for imaging shallow conductors in geothermal fields. Sounds pretty neat. And then the very next day, that Wednesday, Bob Musgrave is going to give a talk on long wave geophysics and Macquarie arc basement. And so that's going to be pretty cool too. And then the following, that very next Thursday, WA is going to be hosting a talk by Adam Smirowski. And that one was postponed. It was supposed to be a live one way back, but COVID came in and he was stopped dead. He's actually going to present from Canada. So good on that. It's going to be some newer technology that is for airborne TM that is helpful for digging into deep and covered targets. And we've got Western Australian examples there, so I'm looking forward to that. If you look at the times, just for fun, I've switched it over to Western Australia time zone instead of the Eastern because, you know, hey, we're out here, we're alive too. So I kind of did that since it's my PowerPoint here. Now, again, I was talking about the the sponsors and everything else. So these are some member benefits that we actually have. There's actually more than this, but I do, these are great ones. So one thing we have is we have a pretty good technical journal, and that's Exploration Geophysics. And what I like about it is it's over a variety of topics. It's not, you know, nailed on something that's just, say, oil and gas or mining or even business. You know, there's plenty of neat stuff there. And it's not just Australia, it's from all over. So that's worth definitely reading. And we also get, of course, preview kind of a chat rag. And that one, if you're like me, you didn't get any copies for quite some time. And I just got April and May in the mail this week. And that's because the publishers were shut down by COVID, but we're back up again for that. Yes, we get reduced entry into the national conferences if you're a member, and you get free entry into a lot of technical events within your local chapter, saying your state there. And like our tech nights that we'd always have here in West Perth, we'll decide, but we may have that start up this September because COVID's way down here, as you probably are aware. Okay, so then job advertisements are good on the ASEG website. And I've taken advantage of the annual wine offers, and that was good wine for a good price. So we get that at a discount. And that kind of segues into the social events, which, you know, not quite happening really so much now, of course, because of COVID. But yeah, it's there. Professional networking is pretty important. I think that's especially the case nowadays, so that's good too. And then research funding and travel scholarships for students. WA has some good stuff there, so that get your friends, students to apply to these. And then the other thing I think is really cool, this is pretty unique, I think, for a society or, you know, organization. We offer free membership for students. Now, you're not going to see that with PISA or ASEG, SEG and things like that. It's pretty cool. And half price for retirees and recent grads. So I do like that. Okay. And of course, like anything, we're on the internet, and we do give out email newsletters monthly, and then all the different little updates as they come. And we have our own website on the internet. We're on Facebook, Twitter, LinkedIn. And the other thing I think is pretty neat, there's an ASEG YouTube page, and they have a ton of webinars that anyone can access across the world. So that's pretty useful, and it's a way to kind of build up your knowledge of different things. And this webinar will be out there maybe by next week. Okay, so with that, I'm pretty close to shutting up. I'm just going to introduce Anshuman Pradhan. Again, as I said, he's from Stanford, and he's a PhD candidate in the Department of Energy Resource Engineering at Stanford. He's a research assistant associated with a whole bunch of different things. One is the Center for Earth Resources Forecasting, the Rock Physics and Borehole Geophysics Project, and their Basin and Petroleum System Modeling Consortia. And he obtained his master's and bachelor's from Applied Geophysics from the Indian Institute of Technology, Indian School of Mines in Dhanbad, India. And Anshuman has had several industry and academic internships where he's worked on applications related to reservoir modeling, seismic conversion, and machine learning, which is, he's gonna kind of synthesize that and present something to us on that. So with that, I think it's time for me to stop sharing, and we'll switch over to Anshuman. So we'll go over there and hit that. And
thank you, Todd, for the introduction. Can you all see my screen? Okay. So once again, I'd like to begin by thanking the Australian Society of Exploration Geophysicists for inviting me to this webinar series. I'm really privileged. And what I will talk about today is, I'll be talking about, the title of my talk is End-to-End Seismic Inversion of Geostatistically Complex Reservoir Models with Deep Convolutional Neural Networks. And this work is done by me and my advisor, Tapan Mukherjee from Stanford University. And before I begin, I'll just like to minimize the screen over here. Just give me 1 second so that I can navigate. All right, cool. Yeah, so as you can guess from the title of the topic, so we'll be talking about reservoir facies modeling, and that will be related to hydrocarbons or petroleum systems modeling. So when I say reservoir facies, I refer to rock lithologies that are commonly encountered in petroleum reservoirs. For example, here we have a cartoon of a reservoir model, a 3D reservoir model. And if we think about conventional clastic reservoir settings, then these rock categories could refer to facies such as channels, plays, shales, and etc. Now, the question that we ask is that why are we doing this? Because reservoir models are routinely used in the exploration and production industry for different kinds of tasks. For example, for production forecasting, and if you want to make strategies about how to place your wells, or even to make decisions about whether to drill or not, reservoir models are very critical. So it's quite necessary that we build reservoir models which are geologically realistic and also agree with the data, with the geophysical data that we have. And that will be the goals of this talk. So I say that in this talk, we'll be trying to constrain our reservoir models to two conditions. The first is that the model should be geologically realistic. Okay, so now let's focus on this geologically realistic part. What do I mean by that? For reservoir modeling, normally we use geostatistical model parameterizations. For example, these are some different kinds of geostatistical models that are available. We at the far end of the spectrum, we have 2-point methods. So basically, you might be knowing this as variogram-based methods or autocorrelation-based methods. So they only honor the 2-point statistics. And as you can see from this image, they do not look geological to me. But as we go down the spectrum, we are trying to honor higher order statistics. And so while honoring higher order statistics, we can capture shapes and features which look very realistic of the systems that we encounter in the subsurface. For example, in this image, you can see that we have channels and levees and splays, which are there, which are easily observed in the outcrops, geologically outcrops that we see all the time. So in this talk, I'll be focusing on this part where we will be trying to generate models which are geologically realistic. For example, object-based models. In this case, we just populate the grid with geologically objects. So for example, we can have a channel object and we just directly populate that into the grid. Saying that, the second goal is that our reservoir model should also honor our seismic data. So these are the two conditions that I say that the reservoir model should honor. Now let's look at some of the conventional approaches about how this is done in the industry. In the industry, typically what we do is that we take our data and then we solve a seismic inversion problem. And this gives us our rock elastic properties. So elastic properties could be PE impedance, S impedance, etc. And then once we have these elastic properties, what we do is that we do some kind of statistical rock physics. We try to model their relationships with the reservoir properties, which could be facies or other petrophysical properties such as porosity, water saturations. And once we do this, this gives us some seismic conditioned facies probabilities. So this is, for example, an example of a 3D model where we have probabilities for different kinds of facies. And then once we have this facies probability model, we can condition our geostatistical algorithms and generate multiple models which honor our seismic data. Now, what are some of the challenges with this kind of approach? Now you can see that since we are solving this inverse problem in 2 different steps, the inverted impedances, they might not be consistent with the geological beliefs. As I said earlier that reservoir systems, they show complex geology, and any of the impedance that we invert from seismic data directly, independently of the reservoir properties, they might not be consistent with the geological beliefs. And also see that we're solving two inverse problems, right? We are going from seismic data to elastic properties, and then from properties to reservoir properties. So when we solve these two inverse problems, rigorous propagation of uncertainty becomes challenging. So what we are proposing in this talk is we want to use machine learning to learn the direct relationship between the data and our target properties. And that is why the term end-to-end. So at one end, we have the seismic data. At the other end, we have the reservoir properties. And we want to use machine learning to directly learn this relationship. So now note that once we learn this relationship, this is just a single estimation problem. So we do not have the challenges that I mentioned in the previous slide. And also, why should we use machine learning? For example, recent advances in deep learning so that we can model very nonlinear functions. And this gives us hope that maybe we'll be able to model this complex geology and also the geophysics of the seismic data. But things are not as rosy as they seem, because machine learning methods, they also come with their own challenges. So here I have listed some of the challenges that are there for effective learning of the statistical model. For example, machine learning, they require large volumes of labeled training data, right? You need training data to train the model, but where do you get your training data from? And also machine learning is prone to overfitting or memorizing the training examples. So we'll talk about this. How do we solve this problem of generating training data, and how do we solve this problem of overfitting as we progress in this talk? So this is an overview of the proposed methodology that we have. We have three steps. The first one is statement of prior uncertainty and Monte Carlo sampling. I'll just give you a brief overview of what it is before going into the details. So in this case, what we do, we generate the training data set for our machine learning problem. For example, we generate volumes of seismic data and volumes of reservoir models, and then try to, for this learning problem that we have, the statistical learning. The second component that we have is that of prior falsification. Note that this data that we generate is synthetically generated, and that's why it becomes necessary to ensure that your real data is consistent with your synthetically generated training data. We'll also talk about prior falsification, and then finally we'll talk about statistical learning, where I'll be using convolutional neural networks to learn the direct relationship between the seismic data and the reservoir properties. Okay, so we'll begin. I'll show this application to an offshore deltaic reservoir, and our study area is a gas producing reservoir in the Nile Delta. And here is a cartoon from the APG bulletin of a geomorphological study that has been done in this reservoir. This reservoir is dominated by Pliocene slope channel systems. And as you can see from this cartoon, different kinds of sand bodies are there in this reservoir. For example, they could include amalgamated channels, sinuous channels, leaved channels. And we also have the presence of thin bedded sands. You can see these cartoons that there are some thin bedded sands which increase the lateral connectivity between this channelized lithology. So correspondingly to all of these facies, we'll be modeling 5 of them. So the first one will be channels, splays, levees, thin beds, and shales. So these 5 will be our target facies that we'll want to model. Let's look at some of the data that we have in this area. We have 7 wells, and at these wells, we have some of the petrophysical logs. So this is an example of the facies interpretation that was given to us by our sponsoring company, which is Edison E&P. And we also have some elastic property logs, for example, PUF velocity and bulk density log over here. Apart from well data, we also have some seismic data. We have post-stack and pre-stack seismic cubes. Okay, so let's begin. And so we'll talk about the first component of our methodology, which is statement of prior uncertainty and Monte Carlo sampling. This is a look at the reservoir grid. So this reservoir zone has an extent of 5 kilometers along the X and Y directions. This map over here is a map of the reservoir thickness. And you can see that the thickness varies greatly. It's about 400 meters at the southeastern part, whereas it can be as thin as 150 meters in the northwestern part. But on average, it has a thickness of 250 meters. So we'll discretize between the top and base horizons. Our grid will be discretized into 250 cells with an average thickness of 1 meter. So the grid we have has about 100 cells and 100 cells along the X and Y directions, and about 250 cells along the depth dimension. And we will be parameterizing this facies by object-based models. Recall that I talked about different kinds of geostatistical models, and we'll be focusing on object-based models. In object-based models, you model each facies, for example, channels and splays with objects. For example, channels will be modeled by sinuous, the sinuous objects, and they can have different kinds of uncertain parameters. For example, the proportion. What is the volumetric proportion of the channels in my reservoir grid? So what we do is that we define some probability distribution. This n over here denotes the normal distribution or the Gaussian distribution with a mean of 30% and the standard deviation of 8%. Similarly, for this object, you can have different kinds of uncertain other parameters. For example, the amplitude of the channels or the wavelength. The wavelength is the distance between two crests of the channel object. And we define probability distributions. For example, this is a triangular distribution. It says that the wavelength of the channel could be between 350 meters to 800 meters. If we look at the thickness, we can see that it's very thin channels. It's about 2 meters to 30 meters thickness of the channels, and so on for the other parameters. We also define similar probability distributions on the other objects. The other objects were splays. For example, splays are modeled as fans. And then we also have levees which surround the channel objects. Then we also have thin beds, which are modeled by ellipsoids. And I'm not showing the distributions that we used over here, but similar probability distributions were used for each of these objects. Now, what we can do is that once we've defined this probability distribution, we can go ahead and do Monte Carlo sampling. And these are two samples from this prior model. And you can see that in this case, we have higher proportion of the channels, and that's why we have greater density of the channels as compared to the sample on the left. Okay, so right now we have defined the prior distribution on the facies. So the next step is to define the prior distribution on the elastic properties. So remember, we want to model the seismic data. That's why we have to model the P wave velocity, the S wave velocity, and the bulk density. We model them by multivariate Gaussian distributions. And basically, these are this is the autocorrelation function which defines the ranges. What is the spatial continuity for each of these properties? Now we can sample this Gaussian distributions. Let's look at some of the realizations of the P wave velocity. So this is the P wave velocity, and the color bar goes from 3000 meter per second on the higher end to 1800 meter per second. This is the S wave velocity, and you can clearly see that shear information will be very critical in resolving the facies, because in the S wave velocity realizations, you can clearly see the channels. And similarly for the bulk density varies from 2 gram per cc to 2.5 gram per cc. Okay, so now we have generated the elastic property realizations. The next step is to forward model the seismic data. And this is our forward model that we use. M over here denotes our elastic properties, Vp, Vs, and density. The forward model we use is convolutional model. Then this is our data. We also model some of the errors. In order to model the seismic data, we did a seismic well tie. The traces in the red over here denotes the observed trace, and in blue we see the synthetic trace. And you can see that we have very good well tie with a correlation coefficient of about 80%, 88%. This was the wavelength that was used for the convolutional forward modeling. So once we have that, we can generate our post-stack seismic realizations, and this is how the two realizations look like for the realizations I've been showing in the previous slides. Okay. So what we've done till now is we have defined the prior uncertainty on the geological model. Then we generated some of the Monte Carlo samples, and basically we have created a training data set for our machine learning problem. But before we can move to train the model, we need to make sure that our prior model is consistent with the real data. And this brings us to prior falsification. Now let's try to understand why the falsification of the prior is essential. Remember that the training data set that we created is by synthetic simulations, right? So machine learning model can perform very good on this data set because it is synthetically generated. But if the real data that was collected in the field, if that is not consistent with our prior model, then the predictions might be biased. Let's see this in practice. We'll look at a very simple example, a 1D example. Let's say we have two variables, x and y, and we are trying to predict y from x. We have some training data from the wells. These are these blue circles over here. And you can see that the training data indicates that it is linearly correlated x and y. So what we can do is that we can fit a linear model, and this is this red line over here. But let's say that our real data now is this red diamond, and it falls outside of our training data. So can you really extrapolate this model and make the predictions? No, because extrapolation is always dangerous. So what we need to do is that we need to ensure, since we have not seen any data in this region, we cannot really make any predictions. So what we need to make sure is that our real data is from the same population as our training data. And that is the prior falsification step. Remember that we had generated all of these seismic cubes. So what we do is that we try to detect if our real data is an outlier. I won't go into the details of how it is done, but here is the reference for the paper. Basically what we do is that we compress them, and we project into a lower dimensional space. All of these gray circles over here is the realizations that we generated. And we also take our real data. This is this red diamond, and project into the space. And you can see that if you look at this plot, you cannot, the real data seems as if it belongs to the same population as the synthetic data. And that means that our prior model is consistent with our real data. And now we can move on to train our machine learning model. Which brings us to the third part, which is statistical learning. So let's see what we will be learning. So coming back to our 1D example, here we learned just a linear model. It was just one-dimensional variables. But in our case, X corresponds to the seismic data, and Y corresponds to the facies model. And interestingly, these models are located on a 2.5 million dimensional space, right? It's a huge space. How do you learn this relationship between this in this high dimensional space? The answer is convolutional neural networks. What we'll be doing is that we'll be using 3D convolutional neural networks to learn this complex relationship between the data and the prediction variables. Now, this network consists of several nonlinear deconvolutional and convolutional layers. For example, let's try to understand what are these layers. Coming back to a favorite example of one-dimensional variables, if it was just a linear model, then we learn just the intercept and then the slope. Right? These are the two parameters that we learn. For convolutional neural networks, the parameters that we learn are these filters. These are called the convolutional filter. Let's look at how these convolutional filters operate. This is a very simple cartoon. We have layer 1 and layer 2. And this is the input image. The input image is 32 by 32 by 3. The convolutional filters, as you can see, are small filters. They are not global filters, but there are some local filters that we have. In this case, it can be 3 by 3 by 3. And what we do is that we try to perform a convolution operation. Basically, we take the dot product and then apply a nonlinear function. This f over here is a nonlinear function that applies to this dot product plus the bias term. And that gives us one output over here. Now we can move around this filter to the next step, and then we can get the next output. And you can also see that we also have a depth dimension, and the depth corresponds to the number of filters. For example, we have one filter, then it will be just one layer. If you have multiple filters, then you can increase your depth. So why is this necessary? Because if you take many filters, then what happens is that you can learn very complex parameters, right? So every layer has, let's say, 32 filters. Then if you have a 10-layer network, then the number of parameters you can learn is about 0.3 million. So this gives us the power to learn very complex relationships and complex geological and geophysical relationships. Okay. So that's all I'll go about the convolutional neural network part. But now let's look at some of the inputs and the outputs to our network. The inputs that we take is seismic data in time, and the output is about the facies model in depth. Before we can move on, there are some other questions that we need to answer. The first is, should we consider pre-stack seismic data, or is only post-stack data enough? The second question is, how much facies can we hope to resolve with the seismic information? In order to do that, we need to look at the well log data. So what I'm showing over here are the 2D contour plots of the well-log data for two properties. On the x-axis, I have P impedance. On the y-axis, I have VPVS ratio. And if you look at all these colors correspond to different kinds of facies. For example, black denotes brine sands, yellow denotes gas sands, and we also have splays and shales and levees. So from a first look, you can see that all of these facies, splays, shales, and levees, they overlap on each other. So this indicates that seismic data won't be able to resolve all these facies. But gas sands and brine sands are well separated, right? So what we'll do is that we will consider three facies, that is brine sands, gas sands, and we'll lump all of these facies together into the non-reservoir facies. There is another part of aspect to this plot. You can see that the VPVS ratio is very important in distinguishing these facies. So the shear wave information will be critical for resolving the facies. That's why we need to also include pre-stack data in our analysis. So the input to the CNN will be our post-stack data and the partial stack data, that is the near stack and the fast stack volume. And then the output will be our facies volume based on only three facies: brine sands, gas sands, and non-reservoir facies. And using our method of training data generation, we sampled 2000 realizations for the training set, validation set, and the test set. Like to highlight that the training set is used for the optimization problem of the machine learning network. The validation set is also used in the training to check whether your model is overfitting. And then the test set, it is completely hidden for validation after the training. This is a look at the CNN network architecture. It looks like a very busy slide, but I'll try to break it down. Let's look at these are all the shapes of the network. The input is the seismic data. This 75 over here refers to the time dimension, 100 and 100 along the X and Y dimensions, and 3 refers to the stack type. We have post-stack, near stack, and fast stack data. So that's our input. Now we use different kinds of 3 by 3 filters, and we also need to use some transpose convolution networks because this is in time, whereas the output is in depth. Remember, this is the output, the 250 denotes depth, and then 3 over here denotes the brine sands, gas sands, and the non-reservoir facies. So we go through a bunch of layers. We apply some transpose convolutions or deconvolution layers to account for the discrepancy between the time and the depth dimensions. And we use about 32 filters in each of these layers. And as I mentioned earlier, this corresponds to about 0.3 million parameters that we can learn. There are also some factors over here, dilatation factors. I'll explain what are these factors. Now recall that the convolution neural networks, it goes through multiple layers, right? And then each of these filters that we have is a 3 by 3 filter. It's a small filter, right? So let's say in this cube, if you look at this pixel, it only looks at a small region in the previous layer. But as you go deeper, you keep on increasing your field of view. Now, why is increasing the field of view necessary? Because we want to capture the spatial continuity of the channels, right? For example, our channels could extend from one corner of the grid to the other corner. So at the end, the network output should see the entire grid. Now, if we go along with 3 by 3 filters, then we'll have to keep many layers, right? So how can we minimize the number of layers we use, keeping the number of filters coefficients same? And that brings us to dilatation filters. Basically, what we do is we expand the filter and we zero pad it. So all of these red circles are the non-zero filter coefficients, and there are zeros in between them. So what happens is that the number of filter coefficients stays the same, but the field of view increases as we go deeper. And this allows us to exponentially increase the field of view for the same network depth. And that is what is happening. In this dilatation factor, we have 1 by 1, but as we go deeper, we keep on increasing our filters by a factor of 2 every time. Okay, so that was our network architecture. This is some of the network training details, how we trained our CNN. The CNN was trained in Python using TensorFlow. And because this was a very data intensive network, we had to use GPUs. We used 2 GPUs and a high amount of RAM. The training time is about 2 days for training this network. But once you train the network, you can get instantaneous predictions. What I'm showing over here is the classification accuracy for the training set, validation set, and the test set after the network was trained. And you can see that we have achieved very good, about 90% of training set and validation set accuracies. Now recall that the test set was kept completely hidden. Our network did not see the test set, and it also does very good on the test set. So this indicates that the network is not overfitting. Okay, so now we can look at some of the results. What I'm showing over here is depth slice from the test case example. On the y-axis, we have inline. On the x-axis, we have x-line. And these colors over here, red denotes gas sands, yellow, which you cannot see, denotes brine sand, and gray is our shale facies over here. On the second plot, I'm showing the CNN predicted gas sand probability from the seismic data. And on the right plot, I'm showing the most likely facies model by thresholding these probabilities. And at first look, you can see that the CNN has done a very good job. For example, if you look at this small thin channel, the CNN has done a very good job at capturing all of these curvilinear features, and it has got right all of these channelized features from the data. Remember, the CNN is predicting just from the data, and the prediction accuracy is about 90%, so it has done a very good job as capturing these complex geological features. Now we can look at some of the cross section. So the y-axis denotes depth again, and the x-axis denotes x-line, and the y-axis denotes depth. Red over here is the gas sands. And one thing particularly, you can see that the CNN has done a very good job at capturing the interaction between the gas sands and the brine sands. So the gas sands should always be at the top and the brine sands should be at the bottom, and the CNN knows to honor that physical relationship. And as before, it has captured all of these small channels. You can see it has captured, and it indicates that there is a high probability that we'll have a gas sand channel over here. So this was for the test case example. Now we'll evaluate the predictions with the real seismic data. Remember that for the real data, we do not have a true model. For the test models, we always have a true model. For the real data, we do not have a true model, but we can look at the data itself. So this is the post-tag seismic data that was sampled into the grid. This is again the CNN predicted gas sand probability, and this is the most likely facies model. And you can see that the CNN again performs very well. For example, we have this channelized feature, and the CNN has predicted with high probability these channelized features. The predictions look a bit noisy, which is expected because the real data itself is noisy. Now we can look at some of the cross sections. Along the cross sections also, the predictions look very good. For example, you can look at this bright spot over here. And this bright spot corresponds to this fluid contact between the gas sands and the brine sand that the CNN has predicted with very high accuracy. And it has captured the same interactions between the gas sands and the brine sands very well. So this was just a qualitative evaluation. Now let's look at some of the wells that we have. How do we do at the wells? So I'm showing over at well 1. On the left plot, I'm showing the gamma ray log. The gamma ray log is at the well log scale. And this is the legacy petrophysical interpretation that was given to us by our sponsoring company. These are all the 6 different facies that we had, but to interest of us is the gas sand, which is in yellow, and the shale is in blue over here. And this is the CNN predicted gas sand probability. And remember that the CNN predicts from the seismic data. So this prediction is at the seismic resolution, but still we have captured all of these channelized intervals. For example, the gamma ray indicates that there is a sandy interval over here, and the CNN predicts high probability in this region, as well as for the second interval at the bottom of this log. Let's look at another well too. Similar results. The CNN has predicted high probability where we have the channelized, like the channel thin beds of the channels. But there are also some problems with the predictions. For example, the CNN predicts very high probability at the top, and where there is no channels over here. So we think that this could be because of edge effects. So we are cropping the seismic data, and that's why, because of these edge effects, the CNN predicts some high probability in this region. Now, finally, we validate our results at a blind well. The blind well was not used in any of the analysis. And you can see that at the blind well also, the CNN is doing a good job. You can see it predicts very low probability of sands where there are no sands. And again, high probability of gas sands where the log data indicates there is gas sands. So this brings me to the conclusions of my talk. what I've shown is that in this talk is that deep convolution networks, they are very effective in conditioning to 3D seismic data, but honoring the complex geological features. So performing a seismic inversion to 3D seismic data while honoring the complex geological model is challenging, but convolution neural networks present an efficient alternative to the traditional MCMC based methods. We found that dilatation filters are very important for capturing large scale patterns with small number of layers, and this lends efficiency to the training of the network. And finally, prior falsification is very critical because we are training our network with synthetic data. So if you want to make reliable predictions with the real data, you need to perform a falsification step of the prior model itself. I would like to wrap up with the advantages and limitations of this approach. You can see that the one advantage of this approach is that the training dataset was generated by Monte Carlo sampling. We did not do any kind of MCMC or inversion. Monte Carlo sampling is easy. It can take time, but it's easy to do. So that is good. And this method has the flexibility to incorporate any kind of model parameterizations, right? So for example, we included object-based models, but since we are sampling by Monte Carlo, we can include process-based models or surface-based models, other kinds of models. But also this methods comes with its limitations. For example, the prediction ability of the statistical model is limited to the training set, right? The machine learning model is myopic, right? It won't see beyond the training data set. Its prediction is always limited to the training data set. And that's why we need to account for all the possible scenarios. And we recommended some methods of doing that. For example, one is the prior falsification, where we ensure that your real data belongs to the same population as the training data. And also we did some kind of error modeling to capture the limitations of our modeling itself. So acknowledgement slide, this work was sponsored was supported by the sponsors of the Stanford Center for Earth Resources Forecasting. So our group works on geostatistical models, but also on machine learning and other kinds of uncertainty quantification methods. And I'd like to thank Edison ENP, who gave us this wonderful data set for this problem. These are some references. If you'd like to find more details about this work, this talk has been accepted for the ASEG annual meeting this year, and I think the abstract should be out this month. So you can, if you want more details, you can look into that abstract. You can also contact me if you'd like to chat about machine learning in general or this talk. For the prior falsification, I have included the paper by Celine Side. It talks about the details about how you can do prior falsification with seismic data. And then finally, for dilatational convolutional neural networks, you can look at this nice paper on this subject by Yu and Colton. So with that, thank you for listening to my talk, and I would be happy to take any questions that you might have.
Okay, let's see. Anshuman, can you see the Q&A button down below for the questions?
Yeah.
Okay, so we can go over. So John Coffin's got a very early one. He was asking, how about including permeability in some of your parameters?
Yeah. So right now we just looked at like static models, but I think this framework can be extended to include permeability as well. But for dynamic modeling, then you'll need to account for flow data, and we need to, I think, think a bit harder about how we can integrate seismic data and flow data together within this framework.
Mm-hmm. Yeah, but that's good. David Annetz has some questions on the CNN. Basically, I mean, you can read through, but he's essentially asking that, you know, can you once you've got your training, how far away can you use this, or do you have to just do it on a very small area and that's it? What's your experience on that, I guess?
Yeah, I mean, definitely like let me go back to this slide where the CNN has a number of different parameters, right? And then you have to tune these parameters. And the way we did was we did hyperparameter tuning using the test set data. Mm-hmm. And it takes some time, but as regards to your question, whether it is applicable to another seismic data, so the prior falsification gives us a very nice way of seeing whether one particular network can be trained. For example, if you have did all of this parameter tuning, and we have one network which does very good on one data set, then we can, then now let's say we move on to another area of the field, and then we can do this kind of training, this kind of prior falsification analysis. So let's say we have another different data set, and then we can see whether it is consistent with the training data that was used to train this network. If it is consistent, then we can go ahead and we can easily use this network. But if it's not, then we'll have to, I think, redo the entire process. We'll have to modify the prior models. We'll have to modify the CNNs also.
Yeah, and of course too, the seismic data could be substantially different. Some might have very different frequency content, phase, et cetera, et cetera. So,
right.
But the methodology should pretty much, you should be able to at least plug and play after a few days once you've got your methodology down.
Right.
That's my
No,
take.
that's correct. I also agree on that.
Okay, and then we've got one that says what all well logs have been integrated.
Integrated, yeah. So for the well logs, we looked at let me go back to the well logs. So we only looked at the elastic logs. So VP, VS, and density. So and then these elastic logs were used to model the variograms. So we had the variograms. So for modeling the variograms, these well logs were done. But all of the simulations that we generated were independent of the well log data. So it was not conditioned to any of the well logs. The well log was used for modeling the variograms and for extracting the wavelets also for the seismic well tie.
Okay. Let's see, no more questions. Let's see, there's a chat. Let's see if someone popped in there. Okay, so someone just said, thanks very much, good talk. Now, some other questions. So now you've got, we'll see if we get any more, right? I have a few that I could ask myself. Yeah. So you have a seismic data set, well logs, and interpretations. Now, did you use the interpreted horizons, et cetera, to kind of base your actual, even your modeling and your test data sets? Or were you trying to go in blind there?
No, we used the interpreted, so the interpreted horizons were used to extract, let me go to this slide. So we had interpretations of the top and the base horizons. And then we use that to extract the seismic data and from that within that section. So, and we had a velocity model for time to depth conversion. And then we converted the interpreted horizons, which are interpreted in depth to time, and then we extract the corresponding seismic section. So we did not account for any of the uncertainty in the interpreted horizons itself.
Okay. Now, since you have all that, just my question, because now you've got a time to depth transposed convolution to kind of do that. That's of course to be very local dependent. And one of the questions I would have then would be how well, if you might pardon the pun, did the synthetics tie your seismic data from the wells that they provided you? Because of course, if their VPVS has errors, density also, then you might have at least a stretch squeeze kind of problem, and or so because we saw you had good results, but they weren't necessarily converging at the exact depth location. So I think correlating that with some of the seismic, adding that information would be helpful for these kind of presentations.
Right. Yeah. So we for the well tie we had about 88% correlation.
Yeah, I saw those. I saw those, but so where you had your differences on your results.
Okay.
And you go back and see, because on the frequencies that we're seeing on those wells, that's in other words, now did you run a normal? There's so many, but you ran some. Did you run some inversions, impedance inversions, and on the seismic, and did those match up with the wells? In other words, was there drift or something like that?
Yeah, I have not compared, because I think we have a legacy interpretation, but I have not compared my results with the impedance inversion. So it would definitely be a good way to check, verify.
Very, very interesting, because it may very well be that what we're seeing as quote errors might actually be what the seismic set is actually seeing, and maybe there's a bit of error in well logs.
Yeah, I'd also like to highlight that the well tie was done at just one well location that was at the center of the grid. That was at the center of the grid. So there could be some time depth discrepancy as we move away from that from that well tie location.
Yep.
So it might be worthwhile to check what are the discrepancies.
Okay, and we've got someone that's asking that he can contact you via email. He's interested in
Absolutely.
the generation of synthetic data sets. That would be fascinating because again, these are your own test data sets that you're doing. And,
right.
Yeah, and it'd be also interesting to look at the seismic test data sets that you've got and kind of overlay them against the seismic that you're maybe stuck with and see.
Right. Sorry, I didn't get that last part. Can you please repeat it?
Oh, I mean, it's kind of up, it's up to you.
Okay.
And then the other, were these runs, they were done on your three angle stacks, right? And not,
right. Yeah.
And did you try this just on the stacks, just to see how much you can extract from that? Because that could be very useful for people if they want to try something and all they have is some things to interpret.
So you're saying that try on different stacks, just look at some of the angle gathered itself, or?
Well, no. Well, first off, I mean, compare your results against just raw stack, or
okay.
The averages of the P and S is just kind of averaged out in the density.
Right.
But it would be very interesting. Yeah, the other one would be very interesting to see whether you're fitting better. Because one thing you have is maybe the nears might have more, let's say, multiples. Maybe the fars might have more remnant ground mole or something like that. So be interesting. Yeah, that'd be interesting to see how they go. And also, typically the nears have higher frequencies, the fars have lower, so yeah, that'd be cool.
Yeah, definitely. So thank you for the session.
Yeah, let's see, we've got any more questions? There's another chat, let's see.
So I just sent my email.
Okay. Yeah. So people, I don't know if people can see that chat or not, but we've got that out there. When we put the YouTube out, webinar out to an MP4 where everybody can listen to us or you talk, we can have that hopefully show up there. And if not, maybe we can do something from ASEG and have it pump it out and stuff like that. Okay. Well, I'm not seeing any more questions, and I don't want to keep yakking away if there's no more questions. But anyway, so maybe we'll wait a few more seconds. But say I'd like to thank you for a very interesting talk. It's kind of fascinating. It does show that this is becoming more and more a very useful tool. You seem to have now, it looks like Stanford is using a almost like a standardized CNN type network scheme and stuff. So this is becoming more and more where these are becoming tools that would be useful. And it wouldn't be just for oil and gas. I'd say this would be very powerful for mining and stuff, where instead of just the frequencies are different, and that the rate paths are not that different though. So pretty cool. All right. So at least for me, I'd like to, on behalf of ASEG, I'd like to thank you for a very interesting talk. What time is it over there, by the way?
It's about almost 10 p.m. over here.
Okay, so not too bad. Okay.
Not too bad, yeah.
Yeah, so
for grad students, it's not too bad. We are used to staying up late doing homeworks.
Well, and I'm assuming you're working from home anyway, so
yeah.
So you can just relax. That's good. All right. Well, thanks a lot, and I think I'll shut this down, and we'll have the next webinar coming up. But we really appreciate this, and we are getting some people saying thank you so much. So really good talk. Enjoy.
Thank you so much for inviting me.
Okay. Cheers, everybody.
Cheers.
So have a good night, and everybody else have a good day here. Bye.
Good night.